discriminant analysis. We're going to kind of blast through this one so we have some time to review. So discriminant analysis is the alternative to logistic regression. Same exact situation, dichotomous outcome, but there's some differences in the uses of it, and we'll go through those. Generally, it's kind of used to predict group membership, but it could be also used to predict survival, passing, dichotomous outcomes, just like in logistic. Yeah. Unlike logistic, though, it uses linear combinations to try to come up with the best function to separate the two groups. And one reason we do need to cover it, because you can always use logistic instead, but we do use it in MANOVA in another lesson. So MANOVA and discriminant analysis are just two sides of the same coin. In MANOVA, we would have to compare an IV. It's two levels of an IV. Discriminant analysis would kind of go the other way and say how do the DVs predict outcome. So it's the same exact thing, it's just done a different way. But it gives you different kinds of information. So for DA, it does some combination of variables predict group membership, and we'll see how that works. For DA, you need a decent sample size, 4 to 5 times the number of predictors. Each group should be well defined. You shouldn't dichotomize continuous measures. So for instance, let's say you decided to do obesity, and you wanted to put them in obese group, not obese group, based on some cutoff of BMI. Well, those are not bimodal distributions. It's a nice normal curve. So you're making a cut right in the middle. That means some people who are just below the BMI cutoff are in one group and somewhere above. Discriminant analysis doesn't work very well when you do that. Some things that we think are bimodal, like self-monitoring, is meant to be a bimodal. You guys ever cover that in social? High self-monitors, low self-monitors. People who are sensitive to the environment, for social environment, those who aren't. Turns out to be a continuous curve. It's not a bimodal curve. Probably a bad concept to do a bimodal. So you need to really have a real clear-cut outcome. It works better when there's a 50-50 split between the two outcomes. If you get an 80-20 split or a 90-10 split, it doesn't work very well. If the predictors are not on the same scales, it's usually worth standardizing them, putting them into z-scores, because the way discriminant analysis works, the different metrics will have some influence on the outcome. With logistic, that's not necessary. There's a lot more assumptions. So normality, like ANOVA, we have to have decent normality, although it's pretty robust to that one. You want, just like last semester, we want to work on outliers. Multicollinearity, it's true for both of them. That should be kind of low, not too much intercorrelation with the predictors. Something. Homogeneity of variance covariance matrices. I'll talk about that in a second. And plus the assumptions of linear regression. So linearity, like with multiple collinearity, interval data, homogeneity of variance covariance matrices from ANOVA. I'll go over that one in a second. The test for that particular assumption is called Box's M test. We'll see that in the output in a second. So let me go through that. So here you have a situation. We saw this a little bit in regression. We're going to just do dichotomous discriminant analysis just with 2 outcomes. You can do it with more, but we're not going to. So this will be an assumption for also for MANOVA. Yeah, maybe.
Do you need a better pen?
Yeah, I don't know if that's better or not. That might be better. So if you have two groups with the outcome, like say a 0 and a 1 outcome, and you have a bunch of predictor variables that are like score variables, you would end up having two matrices for the predictors. Let's say we'll have 4 predictors. On the diagonals would be variances. Let's see, because it's 1 with 1. So here you would just have a variance, variance 1, variance 2, variance 3, variance 4. And the off diagonals you'd have either covariances or correlations. I mean, it's easier to understand correlations even though it actually uses covariances. Covariances are like non-standardized correlations. So this would be the correlation between variable 1 and 2. Remember, these are the predictors. This is the outcome. So that would be the correlation between 1 and 2. It would be an R, 1 and 2, R, 1 and 3, R, 1 and 4, and so on. And you'd have the same thing over there. All right? Can we get this set up? So the assumption is that the overall pattern of correlations and variances is similar enough between these two boxes to not be different by chance than you'd expect by chance alone. And that's called the variance covariance matrix assumption. Variance covariance.
Not similar enough to...
They need to be similar enough to not be different except by chance. If they will never be identical. So the computer computes a matrix-derived index of that by kind of multiplying and dividing all of those variances and covariances with each other. The variances are the same assumption as homogeneity of variance, right? Just like if this was an ANOVA or t-test, we'd assume the variances would be the same. But this one includes both variances and covariances. And the boxes M test is a test of that whole pattern. And that's one that you do not want to be significant. Boxes M is not significant, it means you have not violated that assumption. Now in logistic, this is not an easy assumption to meet. And it is an important assumption, so we have to kind of work on some issues with that.
So it's not very robust.
It's not robust against that assumption. It's pretty robust against normality assumption violations, but not against this one. This is the reason logistic came into popularity, because it's hard to get this to work in discriminant. In discriminant, all the predictors have to be continuous measures, score data. In logistic, that's not a requirement. So the problem we did in logistic with a group being a predictor, you can't really do that in discriminant. It has to really be all parametric, continuous measures in discriminant. On the other hand, discriminant analysis is a little bit more powerful if you do meet the assumptions. So if you happen to have a situation where you really can meet the assumptions, then discriminant analysis may give you significance when logistic might not. So logistic is kind of forcing things into this logit, which is a little less sensitive than discriminant function analysis would be. Yes. Now one problem is boxes M is very prone to be significant for any kind of violation. Even if normality is violated, it will be significant. And sometimes that's a false alarm. So the significant boxes M will lead us down to a little decision tree of some other things to look at to make sure we're okay. Because quite often it will be significant even though you haven't really violated the assumption too severely. And we'll show you how to do that when we actually look at the data itself. Okay, so what we do in logistic is we test the functions versus classification, similar classification tables that we just did. Discriminant is going to give us an equation. It's just like a regression equation, except what you get is a discriminant score. So just like a regression equation, but since this is a dichotomous number, you end up with just a probability, a discriminant score that comes out of this equation. It doesn't do the logistic conversion. And then that score will be used then with a cut point to classify people into survivors, not survivors, pass, didn't pass, just like we did before, to get us a classification table. Excuse me. Now, so what this gives us is an equation, but the equation is called a discriminant function. And it can give us a number of different functions, like in factor analysis. It does a number of solutions to that problem, and then lists them by the number of functions that they have. And there can be n-1 functions in this particular setting. So we'll see when we look at the output how we interpret that. Instead of a Nagle-Karkes R-squared or a regular R-squared, it gives us a canonical correlation, R-squared. Same concept though, gives us percentage of variance accounted for with a canonical correlation.
Can you say that again?
Instead of an R-squared like in regression, capital R-squared, or the Nagle-Karkes one in logistic, this one has a canonical correlation. It's another...
Is that the same thing as the canonical discrimination function?
No, it isn't. So canonical is another word that's used in a different context. So this will be obvious when you see the output. It's just it looks like any R-squared that we're used to seeing.
And it still gives us the
Percentage of variance accounted for in the dichotomous outcome. Yeah. And then we can test these functions with a multivariate statistic that we'll see in a minute. So let's move over to discriminant functions. The DA produces linear equations like regression that predict what group the person would belong to. The predicted value is called the discriminant score. That's that D score I talked about. At the end of each group, at the end, each group is supposed to have a normal distribution of discriminant scores. If DA succeeds well, those distributions won't overlap much. So you form a distribution of the two groups. They shouldn't be too overlapped. If it's working, if it's not working, they'll be overlapped. Discriminant function coefficients table for a standardized canonical discriminant function table. We'll show those in a minute. We'll give the weights. And there will also be a canonical discriminant function coefficient table that gives unstandardized weights like raw regression weights. Those will make more sense when we look at some output. And then we get some things that we're going to look at in a second. Let's not worry about those. There's the discriminant model. We can look at an example, for instance, on the next page, top of 3. This is actually the one they use in the textbook. So let's say you're trying to predict who's going to get an APA internship and who's not. And the predictors are on some exam, a self-evaluation. You say how qualified you think you really are. An exam score, a committee evaluation, and a committee evaluation. So the equation he came up with in this one was a constant. The discriminant score equals 8 minus 8.043 plus 0.703, that's like a regression weight, times the self-evaluation plus 1.75 times the exam score plus 0.092 times the committee evaluation. See those? So for instance, if someone had a 2 on self-evaluation, a 3 on the exam, 3 on the committee, they would get an equation would be minus 0.98. We predict that person would not be successful at getting an internship. It's lower than the cutoff. And based on those, we can do a classification table that we're used to. And I think the rest of these would be better if we just look at the output. So I gave you some output from a big study. I wanted to get a big size study, so I gave you one from the role models. Where does that one go? Here it goes. That's the other one, huh?
The D-score is it always going to be between -1 and 1?
Yes. Yes. Okay, so if you look at this output, I think I do have this. What happened is one of my thumb drives crashed and I couldn't save anything on it, so I had to transfer everything over. And I happened to remember to do it. Some of them I thought I did and I didn't. Let's try and output. All right, we're going to do it on the output I gave you. Sorry, guys. Okay, so this is an example of a big data set where we're trying to predict working status of women. This is an old role model study from the 80s or 70s, but it has a big data set. So we're trying to, the two categories are full-time working women versus housewives, people who stay home, working at home. And the predictors were locus of control, attitudes towards current marital status, attitudes towards the role of women, socioeconomic level, attitudes towards housework.
So, I thought you said discriminant analysis has to be on a continuous variable.
Yeah, all of those were continuous predictors.
Okay, but you still have working and half.
Oh, no, the outcome is always dichotomous.
Oh, it's always.
Oh, yeah, it's the same as logistic for dichotomous outcome. It can be trichotomous too, but we're not going to do those. We'll just use dichotomous. So, okay. So, first thing it does is just to test to see whether the two groups differ, like you're doing in t-tests kind of, or ANOVAs, on the different predictors. And you kind of hope that they do differ, otherwise you're not going to get a very good discrimination. You can see that locus of control wasn't very significant, but the other ones all kind of look significant. So that's just the working versus not working.
So we look at that to make sure that there's a difference.
It gives you some information about where those differences might come. It doesn't tell you how they work together very well, but essentially that's doing a MANOVA between working and non-working on those variables.
Is it a problem with the locus of control?
Well, it's something we might want to consider. If it doesn't work in the equation, we might want to take it out. So it gives us a little bit more information about it. Next thing it does is test the box. Skip one and look at the boxes M. And you can see the boxes M is quite significant, 0.000. So something in that mix is violating the assumption. So here's the things that could violate the assumption. Homogeneity of variance might be violated, because remember we got the V's and V's. So all you would need to have is some violation of homogeneity from one group to the other, and that might show up as a significant boxes M. It could be that the correlations are very different between the two. It could be that there's some lack of normality in some of the variables, that all of those will end up giving you a boxes M. So it's very sensitive and it's not specific.
So if box net isn't specific to homogeneity of variance?
No, it's homogeneity of all of the, it picks up all those things. Variance, covariance, homogeneity of variance, and it's also sensitive to violations of normality, which is unfortunate. So if you get one that's significant, you got to snoop around a little bit more and see if you want to pay attention to it or not. One way to do that is to take something called the determinant of each matrix. Determinant is a number that's derived from all the elements in a matrix. These are two different matrices. There's a series of steps where you actually multiply rows times columns and divide by the inverse. And you get a number that represents a summary of a matrix called the determinant. So the number doesn't mean anything by itself so much, but think of it as a single number represents something about the whole matrix. So it gives you those for the two matrices. And you can see that those log determinants aren't very different, 17 and 16. So that makes us think that maybe those differences are not so serious, or we'll probably do some more snooping around to see how much we want to pay attention to the violation. So we'll come back to, let's assume we're not going to worry about the violation for now. Next output is the canonical correlation. 0.310, that's just like any correlation, 31% of the variance. And the discrimination between working, not working is accounted for by our equation. And it tests whether that's significant or not in the Wilks lambda. Wilks lambda is a multivariate statistic. We're going to see it again in the ANOVA. And we can see that 0.310, essentially the testing is that different from 0. And we can see it's quite different from 0. We're very sure that some meaningful amount of variance is accounted for.
The significance means that it's not different.
And that it is different. The significance means it is different.
So the canonical correlation is 31% variance accounted for. What's this one squared percent of variance that discriminant function accounts for, like an R squared 0.096?
If you do 1 minus the Wilks lambda, you can use that kind of like a eta squared in ANOVA. So Wilks lambda is minus 1 or something like eta squares. So I subtracted 1 minus 0.904, that's where I got the 0.096.
What does that mean?
Down over here. Well, it's another index. It's not the same as the canonical. It's another index of like an effect size.
You got the 0.096 by squaring the 0.31.
No. No, the 0.31 is already, I guess that's right. Yes, that's right. Sorry. Forgot the canonicals are not squared in this one. And
So then it's not 31% of variance?
no, I'm sorry, yeah. Scratch that. It's about 10% of the variance. Scratch that 31%, it's 10%, sorry. In SAS, they square it for you. In this one, they don't square it, I forgot. Yeah, glad you pointed it out. Notice, though, that's pretty much the same as 1 minus the Wilks lambda.
So the test will be squared.
It won't be squared, you'll have to square it. Remember, you have to square it. Yeah, 9.6% of the variance. Yeah. Good. Okay. Next, it gives you the standardized canonical discriminant function coefficients. These are analogous to beta weights in regression. So they're comparable to one another, that means, but you can't say much about a 1 unit increase and so on and so forth about it. So here we can see that attitudes towards current marital status is the smallest one, and attitude towards the role of women is the biggest one. And you can kind of say, well, 8.807 is, like 8 times more than locus of control. They're comparable like beta weights. So those could be useful. Sometimes you use them, sometimes you don't. The next one is the one that's mostly used. These are like factor loadings. So the structure matrix gives you loadings, which is the correlation between the predictor and discriminant function. And that's just like a factor loading where you can kind of weight the function. So the function serves like a factor. In this case, we only saved one function. Sometimes you're going to get 3 or 4 functions. If you want to see what they really mean, they're like latent variables. So you have to interpret those structure matrices to see what would I call it. So in this one we can see attitudes to the role of women is the most positive one, and the negative ones are marital status is the lowest one, and attitude towards housework is somewhat low. While locus control is almost 0. Probably didn't define it at all. I sort of knew that already. Higher socioeconomic status maybe loads a little bit on the positive side. So remember, this was before your generation where attitude of role towards women was actually a controversial topic. Still is some places. So this would sort of fit with those norms of the time. Everybody get that? Okay, then you get the canonical discriminant function coefficients, and these are like the raw regression weights. So these are what actually go into the equation. So if we picked somebody, for example, I just wrote out the equation for you based on those numbers times those particular ones. So for example, if somebody had a locus control of 6, an attitude of 20, the attitude towards marriage of 20, and attitude towards women of 30, etc., we plugged it in. We'd come up with a minus 0.602. We'd see on the two average discriminant scores are minus 0.241 for working women, 0.439 for non-working women, or working in the home, I should say. So we can see that our person would probably come out looking like working on a working scale, right? They're much more on the minus side than the plus side. They're actually lower than the mean of that particular centroid. With me?
So what's that centroid tell you?
Those are kind of the averages of the discriminant scores for each group. So that's
And
kind
then this
of,
is just like almost made up data.
yeah, I just made up.
And then you plugged in, you got negative 0.602.
Exactly.
That's closer to a working score than a houseworker.
Good, great. Everybody hear that? Say it again, that was a good summary.
What was that? The centroid's the center, so when you plug in all the numbers, you got negative 0.602, which is then closer to the working centroid score than it is the housewife. So then it'd be under the working section.
Yep, good.
So these are like the scores.
These are like the scores they got on each of these tests, which is.
Yeah, no, the important point is I just went and made up a typical person that I thought would score this way. A liberated woman. We don't use that word anymore, do we? That's fine. Okay, then based on those scores for each person, remember each person gets a discriminant score, and we can then do a classification table, just like we're used to seeing. In this case, it comes after so I plotted those so you could see that the working women did have kind of a normal discriminant score plot, and the non-working, the housewives also had kind of a normal looking plot. That looks pretty good. And there was some cases of people who didn't classify themselves with either that came out, so forget about those. And then here's the classification table. So you can see we have our working and housewife and predicted and actual observed. Here they call them original. It gives you a hit rate of 65.3%. These are just like the ones we've been doing the very end of the data. Bottom of page 7.
So the original would be what?
Those are really what they are not. No, yeah, so presumably they really are working or not working. We know that about them. And this would be predicted group membership. The idea would be to try to see if we can understand the characteristics of working women versus versus housewives in terms of attitude towards role model and whatever those were important things to them or somebody in those times.
So do those characteristics actually predict whether you're working?
And usually in this case, we're not so much interested in the actual making the prediction. We might be, but in this case, they really wanted to look at those discriminant functions to understand the difference between housewives and working women. So that factor loading was really kind of the most important part of this one. It sort of told us how these groups differed. So the working women were a little bit higher socioeconomic status. They had much more positive attitudes towards the role of women. And those were questionnaires like, can women be adequate engineers? Could a woman be president? Things like that. They had much more positive scores than that. They had negative scores about housework. They didn't think every woman had to be married to be happy. So they had all those things that were kind of characterized of those two groups, which is
How do you get undue cases?
there were some people that didn't classify themselves as working or not working, so in the samples, so we're not worried about those. I didn't mean to. I did a split file to do the thing, and it just came out by the just X that out. We don't care about that. Okay, so
Way back when you were talking about the box, and you said look at the log determinants, and they're relatively equal, so it's probably okay.
Yeah.
What is relatively equal?
if you saw a big difference between them, then you'd want to go look at the. We're going to do this more for MANOVA. We'd go look at these matrices and see. So what if you saw a 0.9 correlation here and a 0.2 here? That's sort of something wrong, right? That means for the housewives, or whichever group this is, the correlation between locus of control and attitude towards housework were not correlated at all, and they were for the other group. That's the kind of problems you run into with discriminant analysis, especially when it's not a random assignment. So you kind of use it to try to decide how well the model worked. But there is no, as far as I know, there's no official cutoff on the log determinants. It would give you a hint of where the problems might be. So you can look at the variances, that's easy. You can do a homogeneity variance test between them, that's easy. You can do the normality. We did see pretty good normality in the discriminant scores, so probably that's not where the violation came from. But again, the boxes M is so sensitive that you almost always get a violation. You have to kind of then snoop around and see where it is.
Okay.
The good news is if you don't get a violation, you're in like Flint, right? Because that means it's not a violation of normality, it's not a violation of variance covariance matrix, it's not a variance of homogeneity of variance. So you know that your data looks pretty good. And sometimes you do get that.
Can I just go back? This box with the percentage, do we worry about this? This talking about the grade. What about the product part?
About the classification. Yeah, okay, so what about?
Do we need to worry about this bottom part?
Oh, those are just percentages of the things above, that's all. Yeah, I mean, it just does it, just calculates the percentages for you, that's all. Just makes it easy.
Going back for the log determinants, do you want those two close together?
Yeah, you'd like-
That way you're at least a 50-50.
No, those being close together just means the underlying mechanics of the two samples are similar. Doesn't mean that they're not different on the things we care about. So you'd want them to be as close as possible.
Okay.
All right, so the concept list, you can see, let's just review that real quickly. We just went through it.
This is the concept of this exam.
I gave it to you in one of the handouts. I think it's right on the front page of this one I just gave you, isn't it? So yeah, so we're going to do a bunch of different concept lists for this exam. This one we're going to just zip through because we just did it. So you need to be able to interpret that output. So all you really need to do is, because I'm going to give you discriminant output and ask you questions about it. So you know what discriminant functions are, what canonical correlations are, the raw and the standardized coefficients, the structure coefficients, the classification table, the Wilks lambda, those are things we just did, assumptions, and discriminant scores. So we just did it, so I'm not going to spend much time on that. ROC curves are pretty easy, just a few concepts. Let's see, did I do this one yet? Something else we're going to get to later. Meta-analysis, we're not doing this time. Those are just tree cutoffs and ROC curves. So, sensitivity versus false positives. You need to know what sensitivity and specificity are. So work on it so no matter how the table comes out, you don't have to come up to me and say, this is reversed from Dr. Mano, I don't know how to interpret it. You've got to be able to do it whichever order it's in. I like her order too, but that's not how SPSS does it. So if we're going to give you some output, you've got to be able to figure out what's the 1, what's the 0, what the 2 are. I'll try and make sure they're labeled so you can see what success or failure is or survival. ROC curves are not many concepts. The area under the curve, where the cutoffs would be the maximize sensitivity and minimize false positives. And what they're used for, they're used with basically classification type data to try and make cutoff decisions. Now the main one we need to review is logistic. And I gave you that list a long time ago. And it looks like Amber stole my content list. Yeah, so hold it up so people can see it. That's the one that has Ankova. Oh, that doesn't have logistic. I gave you a logistic one now. Do we have that?
You would.
I gave you a logistic concept list, right? Pretty sure I did. Nobody have one?
This is the only other one that we got.
Yeah, so that'll have, no, that's not it. I'm going to send it to you. I didn't bring it with me either, I guess. I think Amber took it thinking it was something she could take. Let's see what else. Let's just go through the slides. We can pick out the concepts real easily. We have a slideshow on it. Or if we just look at the output, maybe we should just look at discriminant, some logistic output. So the concepts are when to use it, obviously, dichotomous outcomes.
Which handout are you?
Logistic regression, the slideshow with the output, we can kind of go through that. You can kind of write down the concepts as we go, and then I do have a list. I don't know why I didn't bring it. I guess I brought it in a different folder, but I will send you that. But they're pretty obvious ones. So the -2 log likelihood being the concept on page 2 there, just sort of the summary statistic, kind of like the sum of squares regression, equivalent of like a sum of squares regression. On page 2 of the output, not the slides, but the output. So remember that the chi-square is the the null analysis minus the analysis with the variables in it. So if you want, if for some reason SPSS doesn't give it anymore, but if you subtract 24 from 44, that's what the initial analysis would be with no predictors in the model. Right, so what we mainly care about is that chi-square for the step. That tells us how much the log likelihood went down. -2 log likelihood went down with the entering of the variables in the equation, and whether that's a significant amount or not. So that's like testing our overall model when it says omnibus tests of the model coefficients.
So how much the likelihood, the log,
How much the -2 log likelihood goes down from the step with no predictors in it to the step with all the predictors in it, or however many in this step. For each step, it tells you that. And then the Nagel curve, well, we use either 39 or 51% for the R-square.
And it's step with one predictor in it from all?
From no predictors to all the predictors. In this case, that's how we did it for this one. So that's the meaning. It's a little hard to say what the meaning of that negative log likelihood is. A complicated logit, kind of an equation to get that. We don't have to worry about that. Just think of it as an overall number of how well the model is working from a model with no predictors.
So then the 44, is that considered a high number? Is that a good?
It's hard to say what those numbers mean based on the scales and everything else. They won't mean anything by themselves.
Okay.
But when you look at the 24, the significance of the 24 is what we care about. And it'll differ by different degrees of freedom, but it tests that for you, that the 24.351 is the number that tells us that when we put the variables in the equation, it gave us some prediction that we would way beyond what we'd expect by chance. So that's kind of like in multiple regression, the analysis of variance, equivalent of the analysis of variance here.
What happened?
24.351.
so it puts a variable
I think I'm looking at the wrong number.
Thank you.
Because this is
Yeah.
there.
Page 2 of the logistic, it's the same one with the logistic slide.
Yeah.
You might not have it. But
So
look at,
you said that this 24, so we put the variable in, the equation, what happened?
it's the difference between, like the analysis variance with no variables in the equation, no predictors, and all the predictors. So the numbers themselves you can't really interpret, you just have to look at the significance of them. Tells you what you need to know. And then the R-squares are the equivalent, trying to do that in R-squared version. Hausman-Lemshow table we've gone through pretty carefully already today, so you should know that one. Obvious questions there are about goodness of fit or being able to test deviations in the model. You want that not to be significant. Should be easy ones. Then the classification table, I think we've gone through, you know what those mean for true, false, true positives, false positives, etc. The actual table itself, what are the Wald statistic is a Wald chi-square. It's the B weight divided by its standard error. And that's tested for significance with a chi-squared distribution. Remember, one little caveat is for high B weights, sometimes the numbers are distorted in the significance. Standard errors are not high enough, not low enough. So that's when we use a step. We do it in 2 different steps to make up for that flaw. What we did today, remember that? We did it in step 1, step 2, and we looked at the difference between the 2 steps with that chi-square. That's a better way of doing it than getting the actual significance in here. Usually they'll be fairly similar, but they could be different in certain cases.
So we need to be wary of high wall values.
High B's, high B, high walls are good.
High wall is
That means it's significant, but high B's might produce numbers that are not. I should have probably tried it for IGS 10 here, which has a big negative number, and it was not significant. That one might, if we did it in a step, it might actually be significant.
by taking that out and adding it to the next step.
Exactly. And then we got the charts, all the variables that we talked about. Odds ratios clearly are the important concept here. So just ask you questions about what it means from some output that we give you. The graph doesn't show up very well here, but you get the idea. The idea of the anti-log that we use to find negative values, probably should know that. Just determined. So I won't ask you to interpret a 0.26 odds ratio, but if I give you one that's a negative B weight, I might ask you to go ahead and calculate that as a positive one, so that you can tell me what it means. It'll be multiple choice, so you can see what the answers will be. Okay? I don't think there's very much else on that list, but I'll get it to you. And finally, ANCOVA, which we haven't talked about for a little while, and that one is on that sheet.
Yeah.
So, what are covariants? What are IVs, DVs, and CVs? Versus repeated measures. Remember what that is? So it's kind of a trivial thing, but you can use ANCOVA instead of repeated measures ANOVA by using pre-level as a covariant. So it's something you do see sometimes in the literature, so you shouldn't be confused by that. So if you see an analysis and the decision tree says it should be a two-way with one repeated measure, and you look at the results of it and it says they used an ANCOVA, what they did then, sort of a trick, they used, it's pre and post, they used the pre-measure as a covariant, so if they teased it out of the post measure, let's say it's group 1 and group 2, and then just did a test between these two. So that would be the post measure corrected for the pre-measure. Make sense? It's a way that you could avoid. The reason I used to do it is because repeated measures ANOVA had those, that Binnenfeld had the sphericity, finding Nemo assumption, remember? Which was hard to actually test in the old days before computers could do it. So this was a trick that kind of got around that. But you still do see it sometimes. Sometimes you see it. And you only probably see it in a case with only a pre-post, not a pre-post follow-up. And it gets tricky to do the ANCOVA with two covariates. Okay, what's the next one? Yeah, so remember ANCOVA is much more problematic when you don't have random controlled trials. You have quasi or static group comparisons. Everybody know what those are? Static group comparisons would be like obese versus anorexic versus bulimic, or like males versus females, or like children of alcoholics versus non-children of alcoholics, or groups that are formed that you're comparing. And ANCOVA is going to be a problem when you're trying to use covariates between those, because those groups differ on so many things already. You can't necessarily control for that with covariates. So you need to be thinking about those analyses differently than you do random controlled trials. Even though people do use ANCOVA in those instances, but you need to be wary.
Reduction of the group error versus the use of pre-loss.
Yeah, so the main reason to use ANCOVA is that some covariates adding to within group error, and by controlling for it with regression techniques, you reduce the within group error and therefore increase your power. All right? Well, let's make sure everybody's okay on that one. Yeah. So the best use of ANCOVA is that you've got a regular random controlled trial you're testing. You're testing group 1 versus group 2. And you realize that that there's a lot of within group variance within both groups because of something else. Socioeconomic status, social desirability, some nuisance variable that's making people differ from one another in ways that you're not interested in. Using a covariate then takes away that part of the within group variance. Less within group variance means more power.
So that's probably one of the reasons you would use.
It's the best reason to use it for sure. So in those cases, usually you will meet the assumptions, and usually you'll get a lot more power out of the process of doing it. Now, the one thing to remember though is it also does adjust the means. right? So you don't know which way they're going to go. You might have some nice looking results with your covariate in, and then you tease it out with ANCOVA, and the means move in the direction you don't want them to go, because it will influence both the means. The covariate could influence both the means and the within group variance. You just don't know. Hopefully it doesn't influence the means very much, just reduces within group variance. But it's something, and the way you know that is you look at the unadjusted means on SPSS output are just called, they're just the descriptives, and they're called marginal means in SPSS. Remember that, because it's not printed out as adjusted means. I'll try and remember to actually write it by hand on there so you know that they're adjusted means.
The marginal means are the adjusted.
Yeah, when in the output, the marginal means are the adjusted means. And I think you need to do that in this homework for this time, for whatever time you were doing that. So you can look at that output and make sure.
Assumption/general. Assumption/general.
Assumptions. So the main, we know most of the assumptions already. The new one is homogeneity of regression. And that's the assumption. Sort of similar to this one, except it's a simplified version. If there's two groups, like more than two groups, and you look at the DV-CV scatter plot, this is level IV level 1, level 2. The assumption is that the relationship between the CV and the DV are roughly the same between those.
And when you have a covariate that is not significant, it really didn't have any difference or playing factor in it,
Right. So that's the main thing. So when you look at the output, the variable that's listed doesn't say CV, it says the name of the variable. All that's testing is there a significant correlation between the CV and the DV? It doesn't tell you anything about the difference between your DVs. So that's why you interpret the output as like, do we have a significant covariate? If you don't have one, all you do is lose a degree of freedom. It doesn't help you any. But this assumption is separate from that, which is that the relationship holds constant across the two groups. In random controlled trials, it usually will. In static groups, it often won't. So that's another issue.
I'm just like what Aspen does.
Hmm?
You want to build an Aspen?
Yeah.
Linearity?
Assumption is the scatter plot produces a linear plot, not a curvilinear plot.
Homogeneity of regression.
Oh, I just did that one.
Reliability.
Yeah, there's also an assumption and especially in ANCOVA, that the measures are very reliable.
Magnitude of effect.
So just like in ANOVA, we've got magnitude of effect measures like eta squared, omega squared, D, you can get D, cones Ds, all the same output that we did last semester. Nothing really different about it for ANCOVA.
Treatment times blocks.
Oh, as an alternative to treatment by blocks first semester was an alternative to ANCOVA where you put in a blocking variable instead of a CV. That's it.
So if this is right, the main things that we need to know: discriminant analysis, the logistic regression, ROC curve, and COVA.
So pretty much it's output from all of those with some questions about it. Chi-square was just so you know how to do chi-squares that way. I'm not going to, but you do need to know what chi-squares are when to use them. So remember, don't let me fool you on any situation when there's just two things being compared, be it a correlation or a dichotomous variable versus continuous. You just use the correlation matrix or chi-square to do those. Right? So if I just say I want to know if there's a relationship between gender and group, you could do it with a chi-square. You don't need logistic to do that. Or if I say I wonder what the relationship is between gender and age, that would be a point by serial. And you just look in the correlation matrix. The regular correlation matrix gives you both Pearson's and point by serials. It doesn't distinguish in the process of doing it. So
when you're looking at two dichotomous variables, you just do a chi-square.
chi-square, or there's another one called a phi coefficient that puts it in like correlation type numbers, but same thing. Exactly. Yeah, so but it just is that if you ever need to do chi-squares without having the full data set, I want to just give you an example how to do it. That's what that other sheet was. There's really not much I could ask you about that.